Okay, we're going to talk about Lesson 8, Distributions of Center, Shape, and Spread. Remember, this is in your Module 4 book, so make sure you go to the very end of your big student manual. Don't go to the Module 3, Lesson 8. Otherwise, you're going to look at things we've already done. So, Module 4 starts with statistics and looking at data and stuff like that. So, we're going to do a brief lesson. Lesson 8 is not too bad. If you feel like you understand it, obviously you can skip ahead to the problem set, but if you want to watch the video and get a little bit of review and discussion, then just continue to follow through. This first opening page is not in your student handbook, so I'll talk about it real quickly. It's about reviewing how to do standard deviation. You may have done this in Algebra 1, you may not have. It doesn't really matter. But if we look at it, it says the following data shows the amount of time in minutes spent studying for a math test for 10 students. And you can see the 10 numbers right here across the screen. This is the results of the time that these people said they spend studying. Now, if we review the idea to calculate standard deviation, it says 1, to find the mean, which is we'll state as x. 2 says to find the difference between each data point and the average. 3, square each of the deviations. Find the sum of the squared deviations for step 4. Step 5, divide the sum of the squared deviations by n minus 1, and then D, determine the square root. Now, this is really just a review. For the majority of this lesson, we're not going to actually need to calculate standard deviation, but there is one thing in the problem set that requires standard deviation. It does say you can use technology, so don't worry about this too much. This is just for review. So if we did take a look at it and figure some of it out, if we were to add up all 10 of these numbers and add them up and divide by 10, we get an average of 42. So we'll just make that note. If you don't trust me, obviously add up the 10 numbers and see if you get 42 yourself. Then it says to find the difference between each data point and the mean. And so what they're literally saying you're going to do is you're going to take each number one by one, such as the 34. And so we'll do 34, and we're going to minus 42, and we'll get an answer. Then we'll do 38, and then we'll minus 42, and then we'll get an answer. With that being said, as we do that, we get these numbers as you do that. And again, try it if you're not sure how to do it. Step number 3 says to square the deviations. Those are the numbers that we just got. The deviations is how far we are from the mean. So we would take and square each of these numbers. So for example, if we squared negative 8, we get 64. If we square negative 4, we get 16. If we square 6, we get 36. You could take a moment, pause the video, see if you can state the rest of them. The 19 is rather interesting. But again, as we go across, these are the standard deviations that are in each one. After that, step number 4 says to find the sum of the squared deviations. So that's where we're going to actually take the numbers, 64 plus 16 plus 36 plus 1 plus 16 plus 361 plus 169 plus 16 plus 9 plus 4, and we get 692. So 692 is the result of adding all of these square deviations together. Then we're going to take and divide by the sum of one number less than what we have. So since we had 10 numbers across the top, we're going to take and we're going to divide by 9. So when we divide by 9, we're going to get 13. And then the final step is to take the square root. So the square root of 13, let's see, there's a square root right there. And you get approximately, so the square root of 13 is approximately 3.6. That would be the standard deviation. And that's set up as that design. Now again, that's more for reviewing purposes more than it is anything else. There will be one thing in the problem set where it's going to ask you to find the standard deviation, but you're more than welcome to put that data into your graphing calculator if you have one, or Desmos, or any other technology to use it. Or of course, if you don't have technology, this would be the 6 steps you would use to do that. So what are we talking about in this particular section? We're going to look at sets of data. So the main example that we're going to carry through for example 1, and it goes all the way through like exercise 6 or something like that, talks about battery lifespans. And so in this picture below, they give us a histogram that shows the distribution of battery life in hours for a sample of 40 batteries that were taken of some unknown brand. We're going to study a distribution, or important to think about in terms of shape, center, and spread of the data. And so we're going to look at this data through each particular one as we're looking up here. So in exercise number 1, and of course remember, if you want to answer these on your own, pause the video, go through exercises whatsoever, and then come back and see if you did it right or wrong. That's fine. Or just watch the video where you need help. So it says in number 1, would you describe the distribution of battery life as approximately symmetric or skewed? And so that's where we're basically kind of taking a look at the data. And we kind of look and see, do we have kind of a bell-shaped curve? Like, could we fold this in half and generally get the same thing on the left and the same thing on the right? So if I was to divide this roughly right there, would that be defined as symmetric, or would that be defined as skewed? In our case, for number 1, the distribution is approximately symmetric. Not perfectly symmetric. Understand that there's no really such thing as perfectly symmetric here. It's where we could say generally the right-hand side and the left-hand side are similar in nature. So this side versus this side is similar, not perfect. So we would define that as symmetric. In number 2, is the mean of the battery life distribution closer to 95, 105, or 115? So if we were taking a look at our graph, maybe we make a note of each one. So 95 is roughly right here. 105 is here. And then 115 is here. So they're asking if we were to estimate the mean, meaning if we were to add up these 40 batteries, and we're not actually doing that, we're studying the histogram, what do we think it would be closer to, 95, 105, or 115? It turns out that answer is closer to 105. In number 3, it says consider the numbers 5, 10, or 25 hours as an estimate of the standard deviation. Remember, standard deviation is that thing we talked about in the opening exercise. We're not going to actually calculate it here because we don't have the exact battery counts for hours for each of the 40 batteries. So we're just going to estimate. So they say in A, consider 5 hours as an estimate for the standard deviation. So if we assumed, right, 105, right here would be that piece. If we set a standard deviation of 5 hours, that means we would be considering going 5 hours this way and 5 hours this way. Would that be an acceptable standard deviation for our data or not? That's what we're looking to consider. In this particular case, most of the distances from the mean are greater than 5 hours, so this would not be considered a good estimate for the standard deviation. Let's consider 10 hours. So, right, let's mark again what we're talking about. So if we're talking about 10 hours, we said our estimated average was here at 105. If we consider 10 hours, that means we go over 10 this way, and we go over 10 this way. And we're asking, does this seem like this would be a reasonable deviation from our average and still talk about the data in a meaningful way in terms of acceptability? So it looks like 10 is a reasonable estimate of the typical distance from the mean. It is a reasonable estimate of the standard deviation. So that leaves us with 25, right? Let's just kind of consider that. So again, if we were to take a look and mark our 105 right here, if we wanted to go 25 hours, this would be 5, 10, 15, 20. 25 would go all the way out here, and then 5, 10, 15, 20, 25. Notice how much of the data that tends to cover. It tends to be way more than what we would be looking for in this design. These are kind of like low compared to where the bulk of this data is at. And so when we answer that, of course, we would say nearly all of the data values are less than 25 hours from the mean of 105. So again, this would not be considered a good estimate for the standard deviation. In this exercise, we're going to switch to drops of 55 major roller coasters in the United States in feet. So we kind of look and see what happens. It says in number 4, would you describe the distribution of the roller coaster's maximum drop as symmetric or skewed, and to explain your answer? So look where all our data is at, right? We have some way out here. So if we were to trace this out, this kind of helps you as a visualization. Our data is way down here, and then it kind of goes up this way in that design, where in this perspective we see the bulk of our data is over here. If we were to try and fold it in half, the left-hand side would not generally match the correct side. When the right side, whenever we see that, we call this as skewed. It is actually determined to be skewed to the right, such that that's where the tail is at. So that's important to note, that this side here would be considered where the tail is at, and that's where we decide that it is skewed to the right, because that is where we find the tail. So again, this would be considered not symmetric, but skewed to the right. In number 5 is the mean for the maximum drop distribution closer to 90, 135, or 240. Right? So if we marked them just to consider, see 90. If we mark that on the graph, would be here. If we marked 135, that would be roughly here. And if we did 240, that would be roughly over here. So they want to know what would be the best average for that. And again, we're not calculating this average. We're kind of looking at the graph, the histogram, and trying to decide which one would be the best approximation for that average. So if we took that into consideration, the mean is closer to 135 feet, because 90 is too small, and 240 is a little bit too large for this data set, being that we're skewed. Again, most of the bulk of our data is here. These would be considered outliers. In number 6 is the standard deviation of the maximum drop closer to 40, 70, or 100. So again, remember we said we went with 135. So we're going to make that consideration. If we were to mark 135, and let's take a look at the standard deviations. If we tried to go 40 over, right, 40 would be roughly this way, and 40 would be roughly to here. If we considered 70, right, 70, so about 130, if we estimated minus 60, would take us to about 70. So that would be about here. And if we 70 over in this direction, that'll take us close to 210. Or if we went to 100, right, 100 would take us all the way out to 30. And then that would take us all the way out to about 230. So again, we're trying to figure out which one would we expect to be the best standard deviation. So it turns out, in this case, 70 seems to be about right. The 40 is a little too small. There's a good bulk of data that could be included that was left out. 100 is a little bit too much. 70 seems to be just about right in this case. Now, if we looked at number 7, it says consider the following histograms. Descriptions of 4 distributions are also given. Match the description of a distribution with the appropriate histogram. So really, they're generally asking you to take a look at each of the histograms here. Histogram 1, 2, 3, and 4. And we have the distribution A, which is skewed to the right, a mean of 100, and a standard deviation of 10. B, approximately symmetric, mound-shaped, a mean of 100, standard deviation of 10, and then you can continue to read C and then D on your own. This is pretty much a matching to figure out which one A, B, C, and D matches which histogram 1, 2, 3, and 4. Now again, I would encourage you to pause this video, try to answer it yourself first, and then when you're done, unpause it. I'm going to continue on. We're assuming at this point you have results, and that way you're looking to see. So if we looked at histogram number 1, histogram number 1 is generally symmetric. So we're expecting this to either be B or C. So the question comes down to whether the standard deviation was more appropriate to be 10 or the standard deviation was more appropriate to be 40. So in number 1, we determined this to be, let's see, there we go, to be B. Approximately symmetric with a standard deviation of 10. If we took a look at histogram number 2, this is skewed to the right. So that means we're either looking at A or D. In this case, we turned out to be A. Number 3 is another symmetric one, so that one ends up having to be C, because we already answered the other one that was symmetric. And then that leaves us with D to be number 4. In number 8, it says the histogram below shows a distribution of a gasoline tax per gallon for the 50 states and the District of Columbia in the year 2010. Describe the shape, center, and spread of this distribution. So remember, shape is, do we believe whether it's symmetric or skewed? And then, of course, you want to say whether it is skewed to the right or skewed to the left. Center is, where do you think the mean, the average would be? And remember, the spread for this distribution would be the standard deviation. By how much to the left and right would be appropriate to estimate for this particular data. So again, take a moment, see if you can come up with some ideas for yourself for shape, center, and spread by pausing the video, and then unpause it. All right, I'm going to give you the answers to see how you did. So this one's expected to be a shape that is skewed to the right. So if we look at that, you could argue that this is kind of symmetric, but you got the data, and then it kind of comes off, and then it tails that way. So if you did say symmetric, I can live with that. This one is, if it is really skewed to the right, it's really, really close to being symmetric. So either one is fine. The center is approximately 25, so that would be right here in between 30 and 25. And the standard deviation is about 10. So that would take us generally to about here to about there. And again, you can see that covers the bulk of that data. So if we kind of circle that, you can see that would be the bulk of the data, which is why we would go with 10 for our standard deviation. Last exercise. The histogram below shows a distribution of the number of automobile accidents per year for every 1,000 people in different occupations. Describe the shape, center, and spread of this distribution. Again, I would pause it, take a moment, answer it for yourself, and then come back. Okay, the answers for this is going to be that the shape of this distribution is approximately symmetric. Again, we can draw that. It's nice to draw. We take and we can kind of see this comes up and it goes back down. This tends to be in the middle, and you got an equal set of data on this side, an equal set of data on this side. This one's kind of more obvious to see. The center is approximately 89, right? Somewhere right around there. And if we try to encompass all the data, it states that we would use approximately 10, so that would take us to like 79 off of 89. So that would be to about right here. And if we went roughly 10 to over here, that would take us to roughly 99. And so again, if we kind of circled it, this area right here encompasses the majority of our data. It tends to get lower on each end. So that is lesson 8. If you, of course, need to rewatch any part of the video, rewatch part of the video to whatever extent that you need to. If you have any follow-up questions that the video cannot answer, of course, email me and we'll talk about it. That'll leave you with problem set numbers 1 through 4. I'll have an assignment for that up in Echo, and then you'll submit that in Echo per the directions that I give you in that piece. All right, thank you.